section. So we're actually going to take today and tomorrow to cover this because these are the first of the rules where they start to not be quite as intuitive and really take some practice to see how you apply them. Remember, yesterday we went over the constant rule. We went over the constant multiple rule, the sum and difference rule, power rule, which is pretty darn easy. Bring that exponent down, multiply by the old exponent, reduce the exponent by 1. And then we went over the derivative for the exponential function. And I asked you to, practice those things, make sure you knew what you were doing. And I asked you specifically, try and get done with problem number 9 on 3.1. Oh, before I forget, here's for 2.8. So we've got a couple of starter questions here. So x to the 6th, we could also write that as what squared? X cubed. Okay, we wouldn't normally do that. We wouldn't normally complicate things like this, but we could do it in both directions. And then we've got y equals e to the x. If that's the case, then what's dy dx? E to the x, it's its own derivative. And then if h is equal to 1 over x, what is h prime? Okay, so negative 1 over x squared. And the reason for that was we wrote this as x to the negative 1. We brought the exponent down, so we multiplied by the old exponent, reduced that by 1, so that would be to the negative 2, which would be negative 1 over x squared. Again, there's nothing wrong with leaving it in this format right here. It's just that if we had to use it again, it's probably going to be easier if it's written as that rational expression there. Okay? All right. So again, this section is on the product and the quotient rules. Not nearly as intuitive, and they don't nearly make as much sense as some of the other rules that we've gone over. And it would be really nice if the derivative of a product were the product of the derivatives. Like find the derivative of each one of the functions and then just multiply that together. Okay, not nearly that simple. Okay, please don't do that. Here's the product rule. So if we're finding the derivative of f times g, in words we say it this way. It's the first times the derivative of the second plus the second times the derivative of the first. So we're going to do the first, which is f of x, times the derivative of the second, which we're going to write as g prime of x, plus the second, that's going to be g of x times the derivative of the first. And again, I like phrases. There are lots of phrases that I've used for years. I still remember one that I learned in a linear algebra class where I came up with a way to remember how to find the inverse of a matrix. And I've always kept that phrase. So I think if you've got a phrase that describes what needs to be done, sometimes that's easier than doing it symbolically, okay? One of the ways that you could remember this is you could look at this and say, well, I've got f and g are part of the original product here. Each one of these gets its turn being differentiated. So f stays a regular old function. G is differentiated. So we get f times g prime of x. And then we leave g alone and we take turns differentiating f. So it's g and then f prime of x. And if you kind of keep it in mind that way, toward the end of this section, you'll see another way that we can apply that. So I'm going to attempt to run through a quick proof for this. This is what we're going to start with. We're going to start with the definition of the derivative. So that's the limit as f of x plus h times g of x plus h minus f of x times g of x all over h. And then we're going to do kind of a clever trick. So here's the trick. Okay, I'm just going to draw a big long line. Might need to make it longer by the time we're done. Just going to rewrite this stuff. Okay, again, just working with the derivative. Got that over h. And then here's what I'm going to do. I'm going to subtract f of x plus h times g of x. And I can't just do that without compensating for that somehow. So I'm going to add the exact same thing back in. Isn't that still exactly what we were working with here? Just looks different. I subtracted this quantity, and then I added that quantity back in. If I wanted to simplify here, I could cancel the two of those. I'm right back where I started. And why on earth would we do this? Well, let's take a look. We're now going to reorganize these in kind of a special way here. So I'm going to take this and I'm going to write f of x plus h, g of x plus h, minus f of x plus h, g of x. And then I'm going to gather these other guys together. So this is going to be minus, let's see, and that was a plus. I'm going to write that plus one first. So this is going to be plus f of x plus h, g of x. And then I'm going to write this minus term right here, minus f of x, g of x. All of that over h. So I collected this one and this one together, and I collected this one and this one together, and I put this one on the tail end of it. Everybody see where those came from? Maddie, you're crinking your nose. I see. Do you want to move closer? Okay. All right. Okay. Any questions to there? Yeah. No, I put the yellow ones in front. They're right here. Okay. And I took these blue ones and I put them on the end, but I put this one behind there. I put the minus one at the end. What's that? I'm gonna show you right now. Okay. So I'm gonna rewrite this now as f of x plus h, g of x plus h, minus f of x plus h, g of x all over h, and then I'm going to write plus f of x plus h, g of x minus f of x, g of x all over h. Does anybody see why now? What do these have in common right here? Okay. So on that first one, I've got an f of x plus h. I'll tell you what, I'll write it down here. I think I've got room. So I'm going to take out an f of x plus h. And what I'm left with is a g of x plus h minus g of x. And it's okay for me to just put that over h. Doesn't this represent that same thing right there? I'm going to do a similar type of thing here, but what am I going to take out on this one? I'm going to take out a g of x. So I'm going to write plus, and I'm going to take out that g of x. So I've got g of x, and then I've got this fraction f of x plus h. And at this point, I'm hoping that this is starting to look a little bit familiar. What have I been leaving off as I've been doing this work here? A limit. So if I slap that limit back on the front there, so if I do the limit as h approaches 0 and the limit as h approaches 0, okay, let's write down what each one of these equals. Okay, as h approaches 0, what does this turn into? F of x. As h approaches 0, what does this turn into? That's the definition for the derivative of a function named g. So this is g prime of x. And does this have an h in it? Nope, I could have pulled that out front if I wanted to using the constant multiple rule. So that's going to be g of x. That's what that is right there. And what is this in the limit as h approaches 0? F prime of x. So what I get here is I get f of x times g prime of x. And then I get plus g of x times, this was f prime of x. Couple of clever tricks along the way, just a bunch of algebra. We're working from the definition. This really isn't calculus until you get right here, until you start taking the limit. You'd have to know what a limit is. You'd have to know that as h approaches 0, this approaches x, so this would just be f of x. You'd have to know that this in the limit as h approaches 0 turns into g prime. It's the definition of the derivative. But the rest of this stuff, the hard work, the heavy lifting on this, just algebra. You could teach probably a 9th grader to do this pretty easily. They wouldn't like it. You might have to pay them, but you could do it. Okay, any questions there? Okay, so now we've got a rule for finding the derivative of a product. So one of the hard parts about calculus is looking at something and knowing which rule you need to apply. So let's take a look at this. I have a function right here times a function right here. If it's a function times a function, you can use the product rule to find the derivative. So let's go ahead and do that. So the derivative of a product is, it's the first times the derivative of the second plus the second times the derivative of the first. So let's identify each one of these. This is the first one and this is the second one. So that means y prime is going to be the first one, which is x squared, times the derivative of the second one. So all I need to do is just look at 1 minus 2x, and what's the derivative of 1? 0. What's the derivative of minus 2x? Negative 2. Plus the second, which I'm just going to blindly rewrite, so it's 1 minus 2x, times the derivative of the first. And since the first is x squared, what is the derivative of x squared? 2x. Okay, now we wouldn't want to leave it this way. We're going to want to simplify to a reasonable degree. So this is going to be minus 2x squared. This is going to be plus 2x and then minus 4x squared. So if I put this all together, I get y prime equals, let's see, what have I got there? Negative 6x squared plus 2x. Is that right? Okay. Does anybody recognize that? Oh, so disappointing. So disappointing. That's problem number 9 from 3.1, the one that you were supposed to do last night. Yes, it is. Okay, that's problem number 9. Okay, now, using yesterday's tools, the only way that you could do this was write this as a power function. So if I go through and I rewrite that as x squared minus 2x cubed, and then differentiate it using the power rule, I get y prime equals 2x minus 6x squared. They're the same thing. Okay? Now, just let's make a point right here. Which of these two is easier? By far, this is easier. Okay? What we did is we did some very easy algebraic simplification, then we did the calculus. On this one, we did the calculus first, then we did the algebraic simplification. Nearly all the time, it's going to be easier to do the algebraic simplification, if there is any to be done, then do the calculus, than in the other order. Okay? So if you've got an option to simplify something, simplify it algebraically, then do the calculus on it, then do the derivative. Okay? That's nearly always going to make your work easier. Okay? But with that said, take a look at problem B on example 1. Can you do any algebraic simplification? No, you're stuck. You are absolutely stuck. This is that function times that function. It's 2x times e to the x. So there's no way to simplify this, so you have to use the product rule. So it's going to be the first times the derivative of the second. And what is the derivative of the second? E to the x. Plus the second times the derivative of the first. Just look at the first, it's 2x. What's the derivative of 2x? 2. So one way you could write it would be 2x e to the x plus 2e to the x. Another way that you could write it, okay, there's nothing wrong with this, okay, but if I had to evaluate that at, say, 2, I've got to plug a 2 in here, here, and here. It might be a little bit easier to do it this way. Let's take out a 2 and an e to the x, and you're left with an x plus 1. That probably is a little bit cleaner form of the derivative. Okay, any questions? Okay. Yeah.
What rule did you use for the second part? Like, you could have 2x times e to the x plus e to the x.
Use the product rule.
No, not the product rule. The constant. Is it the constant?
For the 2. Yeah. So we're looking at this right here as a function of 2x and a function of e to the x. So what's the derivative of 2x. So there are a couple ways to think of that. If you just think of just that, it's a line with a slope of 2. So if we're talking derivative, its slope is 2 everywhere, so its derivative would be 2. If you thought of it as a power function, bring the exponent down, so that would be 2 times 1. Reduce the exponent by 1, that would be 0. So 2 times x to the 0 would be 2 times 1, so it would be 2. Got it? Any questions? Okay, so that's the product rule with a proof and 2 applications of the product rule. Now we're going to do something called the quotient rule. And what I've got here is, again, I've got a phrase that describes how we find the quotient rule. Okay, so it's going to be the bottom times the derivative of the top. Well, the bottom is g of x. The top is f of x, so it's going to be g times f prime of x. Then notice it's got a minus in here. This is not a plus. Many times in math, multiplication is associated with addition and division is associated with subtraction. So it's a minus. Then it's going to be the top. So that's going to be f of x times the derivative of the bottom. So that's going to be g prime of x. And then here's the interesting part. We take the bottom and we square it. So this is going to be g of x squared. Whatever that bottom function is, you're just going to take that and square it. So the derivatives more appear in the numerator, and the bottom is just the bottom squared. Okay? There's a fancy little phrase. I'm not a fan of, singing Heidi Ho and stuff like that. But if you say it this way, if you want to remember it this way, that's fine. Low-D high minus high-D low over low-low. So low would be the bottom, high would be the top. So low is the bottom. D high, that's what does a big D stand for? Derivative. So the derivative of the high one, the top one. Okay. Minus high, that's going to be the top one. D low, derivative of the bottom. And then low, low, bottom times bottom or bottom squared. Okay. I don't care how you remember it, but you better remember it and you better get it right. Because when we take a test on chapter 3, it's going to come in 2 parts. On the first day, I'm going to hand you a couple pages of paper, and it'll have 10 or 11 problems on it, and the instructions are the same for every one. Find the derivative of these nasty functions. So if they're quadratics, if they're polynomials, if they're exponentials, if they're trig functions, if they're hyperbolic trig functions, all sorts of stuff, you're going to need to know the rules. And if they're quotients or products or whatever they are, you've got to be able to find the derivative. Okay? So I don't care how you remember the rules we go over. You've got to remember them and you've got to practice them enough that you can apply them in different situations. Okay? Any questions there? Okay. We're going to run through a quick proof, and like any good mathematician, we're going to use something that we already know how to do. So here's what we're going to do. We're going to start with this function right here. Any generic function that's defined as a quotient. So h is defined as the quotient of f over g, and we're going to apply the product rule. So in order to apply the product rule, I've got to make this a product. So here's what we're going to do. I'm going to write this as h times g, and that equals f. All I'm going to do is just rewrite h, hope this isn't freaking out. We'll try it one more time. Good, we're sticking around. G times h equals f. Okay. All I've done is algebraically move this around. Okay, now I'm going to find the derivative with respect to x. So I have a product over here. So let's go ahead and apply the product rule. The product rule is the first times the derivative of the second, plus the second times the derivative of the first. And over here, I'm just finding the derivative. So that's going to be f prime. Any questions? Okay, now what I wanted was h prime of x. So I want to get h prime all by itself. So let's move this around and let's get h prime by itself. So if I do that, let's see, I'm going to move this to the other side. So that's going to be gh prime equals f prime minus hg prime. Again, it's just an equation. Algebraically manipulated the equation. Did some calculus on both sides of the equation. Same thing on both sides, so that's algebraically legal. And then I'm just moving this around so I can get h prime by itself. If I want h prime by itself, what do I do next? Divide both sides by g. So if I divide both sides by g, here's what I've got. I've got h prime equals f prime minus h g prime over g. Well, the only thing that I don't like about this is notice that I've got h prime on one side all by itself, and over on this side I've got an f prime, a g prime, and a g, all parts of the way the original function was defined. What I don't like is this guy right here. I don't like having an h involved there. Any ideas? Yep. So we're going to do f prime minus what h is equal to. H is equal to f over g times g prime over g. Yeah.
Why don't we like the h?
Because h is defined in terms of f and g, so we might as well get everything over here in terms of f and g. What do I do next? Okay, take a look at your paper there. If I were going to take this and I were going to simplify this, I wouldn't want that fraction in the numerator. I would want to simplify this. Technically speaking, this is a complex fraction. So I'm going to get a common denominator, and that's going to give me g f prime minus f g prime over g over g. And since there's a fraction on the top, I might as well think of the bottom as a fraction, so I'm going to put that g over 1. And then I never divide by a fraction. I'm going to take this and I'm going to flip it over and multiply. So I'm going to multiply by 1 over g. So if you'll notice, the end result of all this is g f prime minus f g prime over g squared. G f prime minus f g prime over g squared. So we proved the product rule, and then we used the product rule to create the quotient rule. Again, I don't care how you remember it, but you have to remember that. And you have to be able to look at a function and figure out, hey, if this is a quotient, I've got to use the quotient rule here. I can't just, differentiate the top, differentiate the bottom, and then call it good. Okay? Any questions? Okay. So let's take a look at these examples right here. These are applications of the quotient rule, so take a good look. This is the top, and this is the bottom. So that means the derivative with respect to s would be, let's see, this said it's got to be the bottom, and I'm going to do this. I'm going to move that negative up on the top. Okay, so we're going to think of the bottom as a negative 3s. So it's bottom. Bottom is s to the 7th times the derivative of the top. What is the derivative of negative 3s? So we're taking the derivative with respect to s. What's the derivative of negative 3s? It's negative 3. Okay. Minus the top, which is negative 3s, times the derivative of the bottom. And what is the derivative of s to the 7th? 7s to the 6th. All over the bottom squared. So the bottom squared would be s to the 14th. Okay, so let's do a little bit of simplification here. This is negative 3s to the 7th. This is going to be plus 21s to the 6th, all over s to the 14th. Yeah. Oh, to the 7th, you're right. Yep, to the 7th. Yep. Thanks. And then what would we want to do with this? Yeah, we've got some like terms here. So this is going to be, what do we got here? 18s to the 7th over s to the 14th. So I can cancel those 7 with 7 of those. So this is going to be 18 over s to the 7th. Any questions there? Any mistakes? Okay, let's take a look at this. Could I do some algebraic simplification first? Sure. let's rewrite this as, well, I can cancel this with that. That's going to be the sixth power. So this is negative 3 over s to the sixth power, or wouldn't this be negative 3 s to the negative 6? Then if I do some calculus on it now, multiply by the old exponent, reduce the exponent by 1. So this is going to be 18 s to the negative 7, or 18 over s to the 7th. A lot easier doing the algebraic simplification first. Okay? But this is a good exercise because do we get the same answer in both cases? We do. And that's one of the cool things is we are far enough along in math that there are lots of different ways to approach a problem. And the beauty of it is, regardless of which way you do it or how you approach it, as long as it's a correct method, we should arrive at the same place, even if there are 14 different roads to get there. Okay? So if we look at this problem right here, this is an interesting one because I could go through and I could do it this way. I could say, you know what, it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. But you could do it that way, right? This would give us, let's see, we'd have 2x squared minus 2x. This would be, help me out here, this is minus x squared, correct me if I'm wrong, and then this is going to be a plus 1 all over x minus 1 quantity squared. And if you take a good look at that, isn't this x squared minus 2x plus 1 over x squared minus, or x minus 1 quantity squared? Anybody recognize that? Isn't that x minus 1 quantity squared? So wouldn't these cancel each other out? And wouldn't we end up with a 1? So after all of that, yeah. Okay. After all of that, the derivative of this is 1. What if we did this? What if we algebraically simplified first? X minus 1, x minus 1, or sorry, x plus 1, okay? Cancel this off. This is the same as x plus 1. Now let's find the derivative. Oops. G prime of x would be 1, just like it was here. A lot easier doing this method. There is one thing you'd want to be aware of in both cases. This came from a rational function. Is there anywhere where this function is not defined? At x equals 1, okay? In fact, we have a point of discontinuity at x equals 1, don't we? In this particular case, we have a hole. If you have a point of discontinuity, is the function differentiable there? Nope. So we'd want to include a little domain restriction, say x can't equal 1. Any questions? Okay. So if you have a choice of doing algebraic simplification first, then doing the calculus, 99% of the time that's going to be better and easier than trying to do the calculus first. Okay, but there are times, take a look at the next example, where you don't have the option to do the algebraic simplification first. You can't algebraically simplify it, so you are stuck. And in those cases, you're going to have to use, in this case, the quotient rule. Same thing here. Even though these are polynomials, there's no simplification that can be done. So let's find the derivative here. Bottom, blindly write it down. Better to write it down in parentheses. Times the derivative of the top, 3e to the x. Minus the top. Again, you'll notice I'm using parentheses a lot. Really good idea for the most part. Times the derivative of the bottom, 2x. All over the bottom squared, so that's going to be x to the 4th. I really wouldn't skip much more work than that. I'd get in the habit of writing down the bottom in parentheses, the derivative of the top in parentheses, and so forth. It's especially critical here when you have more than one term over here and some things to multiply and distribute through. That minus is important. You better make sure that you get that right. People typically make mistakes there. Any questions? Okay, listen very carefully. We're done with calculus on this problem. But we're not done with the problem because we need to simplify this. Okay? So if we take a look at this, I could multiply through and get 3x squared e to the x minus 6x e to the x, and then put all that over x to the fourth. Yeah. Okay, it would be much better if we factored out the 3e to the x, and is there anything else I can factor out? I can factor out an x. So I'm going to take out, whether it's from here or from here, a lot easier to do it from here, 3x e to the x. I took out the 3 e to the x and an x, so I'm left with 1x. What's left of this? Just a 2, a minus 2, and then in the denominator, an x to the fourth. Are we done simplifying? Nope, because I can cancel that x with one of those. So here's the final answer. 3e to the x minus 2 over x cubed. And that's probably what we'd say simplified to a reasonable degree. Questions? Okay. Again, I can't do any algebraic simplification. So if I figure out what dy dx is here, there's the bottom, there's the top. Okay, would you go ahead and write that down? Don't do any of the algebra yet, just do the calculus. Bottom, write it in parentheses. Derivative of the top. Let's stare at 2x plus 5 for a second. The cool part about this is you really get to completely ignore all of this stuff and just look at 2x plus 5. It's kind of like chunking or just compartmentalizing. We need the derivative of the top. 2x plus 5. The derivative of 2x is 2. Derivative of 5 is 0. So this is just a 2. Minus, that comes from the quotient rule. Top, write it down in parentheses. Times the derivative of the bottom. We're just going to look at 3x minus 2 for a second. Derivative of 3x is 3. Derivative of negative 2 is 0. So that's a 3. And then we just write the bottom down and we square it. Calculus is done. Now we're going to distribute through here. Distribute through here along with the negative. So here's what we've got. I've got 6x minus 4, and then I've got minus 6x and minus 15. Is that right? Really don't have much to do with the denominator. We're hoping to get a common factor. Maybe we can cancel something off. So the 6x's cancel off, so that's gone. So I end up with a minus 19 on the top, and I have a 3x minus 2 quantity squared on the bottom, and that is it. Any questions? Okay, then let's take a look at the next one. So we've covered all of the ideas that we need to in this section, and the rest of this is just practice, and you'll see down at the bottom of this page, we've got another type of problem that we're going to figure out using either the product or the quotient rule, but we'll get there in just a second. Okay, we want to take a look at the problems right here. This is more typical of what you'd see. These could easily be on the exam that I'm going to give you in a couple weeks. Okay, can you find the derivative of some ugly function that looks like this? And it says use any appropriate method. Suppose if you wanted to do this from the definition of the derivative, you could if you wanted. Okay, but that would be a huge pain. We're going to find the derivative with respect to x. Remember, variables are toward the end of the alphabet. Letters toward the beginning are going to be constants. So this is really a constant. You could treat that as a constant. Okay? So the first question when we see something like this is, this looks really ugly. Can I make it any simpler using some algebra? Yeah, you could. If you know how to do that, that's great. If you don't, here's what you're stuck with. This would be a quotient. Okay, watch carefully, please. Y prime would be the bottom times the derivative of the top. Derivative of x would be 1. Derivative of a, since it's a constant, would be 0. So that's just a 1. Minus the top which is x minus a, times the derivative of the bottom. Square root of a is just a number, so that's a 0. What's the derivative of the square root function again? 1 over 2 times that same square root. All over the bottom squared. And the bottom squared would be square root of x minus the square root of a, quantity squared. Does that turn out to be x minus a? It does not. Please don't screw that up. It's a binomial. It will have a middle term. Then we can go through and we can algebraically simplify that. So you'd have to get, well, gosh, we'd have to figure out a common denominator on the top, a whole bunch of stuff. Be a little bit nasty. Do you want to do that? And this is where algebra comes in really handy. One, how do you factor the top? You could rationalize the denominator. You could do that. Okay. Michelle? What do you mean reciprocal? So same thing, rationalize the denominator. Okay, you could do that. Yeah. It is. Aren't those two perfect squares? They're not ones we typically think of, but wouldn't that be the square root of x minus the square root of a times the square root of x plus the square root of a? If you've got two terms, you can always write them as, or a difference of two terms, you can always write them as two conjugates, a factoring of a difference of squares. X is a perfect square of the square root of x, and boy, that comes in handy here. A is the perfect square of the square root of a, and that comes in handy here. So if you multiplied the two of these together, this is what you'd get in the numerator. And look at the advantage we have here. I can cancel that off. So this is an algebraic representation of the original problem. No, I haven't found the derivative yet. Now let's find the derivative. What's the derivative of the square root of a? Square root of a. 0. What's the derivative of the square root of x? 1 over 2 times the same square root. Okay, that's the answer. So guess what would happen if you went through the pain of simplifying this algebraic expression? You get that right there. Both are perfectly valid techniques. Okay? And I show you this because most people would not think to do it this way. If you want to rationalize the denominator, correct me if I'm wrong, but I think it gets a little bit more ugly because then you'd have an x times the square root of x or an x to the 3/2. Yeah.
Well, the way I did it, I multiplied it up.
Mm-hmm. And then you canceled?
Yeah, and then I just canceled. I didn't actually multiply it up on the top.
Okay. And if you see that you don't need to multiply them through, then that works very well. Okay. But if you're in the habit of, gosh, I'm rationalizing the denominator, I'm going to multiply everything through, you lose that common factor, and then you're in a big mess. Okay. So if you know your algebra, okay, whether to finish this off or really this technique right here, this is really an algebra-dependent problem. Okay, because simplifying this is going to be very difficult. Simplifying here, nice nifty trick, and look how easy the calculus is after the fact. The only calculus occurred right between here and here. That's it. Here you got a bunch of nasty calculus and a bunch of algebra to simplify it. Okay. Any questions there? Okay, let's take a look at the next one. It's this function times that function. So we could use the product rule and we could find u prime by doing, remember, it's the first times the derivative of the second. So x minus 1 over x. What's the derivative of the second? What's the derivative of x? 1. And what's the derivative of 1? 0. Plus the second, x plus 1, times the derivative of the first. Well, the derivative of x would be 1. What's the derivative of negative 1 over x? Negative 1 over x. Look at the starter question. the derivative of 1 over x is negative 1 over x squared. So what if there was already a negative in front of it? Positive 1 over x squared. And then we have to do a bunch of algebra here. Wouldn't it be easier to do this? Let's see what happens. May seem a little bit strange, but that's an easy function to differentiate. That's an easy function to differentiate. What do you get when you multiply negative 1 over x times x? Negative 1. And then at the very end, we get a minus 1 over x squared. Okay, now let's find the derivative. What's the derivative of this term? 2x, just using the power rule. What's the derivative of this one? 1. Again, just using the power rule if you want to think of it that way. What's the derivative of negative 1? 0. And what's the derivative of negative 1? Whoops, that should just be an x. I was thinking ahead. Thank you very much. Okay, what's the derivative of negative 1 over x? Positive 1 over x squared. So guess what happens if you go through here and you simplify? You'll get this expression right here, just for the fun of it, since this one's not too bad. Watch what happens. Distribute through x, 1 over x. This one would be x, and this would be plus 1 over x squared. Whoops, that's just 1 over x, isn't it? Yep. Let's see, we got that. Yep, doing here. And then we've got a 1, and then we've got a plus 1 over x squared, right? So I get these 4 terms right here from those 2 binomials. And let's see what we've got here. Those 2 x's, there's our 2x. These 2 are exact opposites, so they cancel to be 0. There's our 1, and there's our plus x squared. So we do get exactly that. Again, much more difficult to do it that way. A lot easier to do the algebraic simplification first. Okay, any questions? Yeah. Yeah, it would be wise to keep track of what the domain issues were. If you couldn't plug in a 0 to begin with, you can't plug it in the end. And what would not be okay here? Oh, yeah, it's got to be 0 and it can't equal a. Okay? So x has got to be greater than 0 and it can't equal a. All right. Okay, so we'll see if we can finish this right here. And then what I'd like you to do between today and tomorrow, you can get started on the assignment. The rest of the stuff, we're just going to look at practicing these techniques in somewhat unique situations. So we're going to use the product rule right now to come up with the derivative of a very useful function. So if I have y equals e to the 2x, okay, the derivative of e to the x is e to the x. The derivative of e to the 2x is not e to the 2x. Okay? It's not how we do it. But we can figure this out by rewriting this as a product. So if I have y equals e to the 2x, is there another way I could write that so that instead of being a composite function, it's a product of 2 functions? E squared times, or you're on the right track, I think. Isn't that e to the x squared? And isn't that e to the x times e to the x? Again, we normally don't make things more complicated. We're much better at going this direction, going to the left, than we are to going to the right. But this is more advantageous for the time being because this is now a product. Now, let's figure out what y prime is. This is the first function, and that's the second function. So we're going to have a lot of e to the x's floating around here. First function is e to the x times the derivative of the second function. So what's the derivative of e to the x? E to the x. Plus the second function, e to the x, times the derivative of the first function, which is e to the x. So what's the derivative of e to the x again? E to the x. So what I have here is e to the x squared, or e to the 2x, plus e to the 2x, which is 2e to the 2x. So if I have a constant times x, e to a constant times x, that constant stays in the exponent, but it's also repeated as a factor out front. So if I'm finding the derivative of e to the kx, that constant stays in the exponent, but it's also repeated as a factor out front. So the derivative of e to the kx is k e to the x. So what's the derivative of e to the 3x? 3e to the 3x. So what's the derivative of e to the negative 2t with respect to t? Negative 2e to the negative 2t. I've got a constant multiple here, so technically it would be 5 times the derivative of e to the 4x, which would be 4e to the 4x. But we can just write that, we'll pull that constant out front. It's repeated as a factor out front, so 20e to the 4x. And what about this one? Yeah, the constant sitting out front of the x is a negative 1. So we'll have a factor of negative 1 out front and repeat that in the numerator. So this is going to be negative 1 over e to the x if we wanted to evaluate that. That might be a little bit better. Okay, any questions? Okay, watch for just 1 second. What if I wrote this as 1 over e to the x? And I said find the derivative of this. Isn't this problem equivalent to this problem right here? Right now it's a quotient. Okay, watch. You don't have to write this down if you don't want. You can just watch. Bottom times the derivative of the top. 0. Minus the top times the derivative of the bottom. All over the bottom squared. So this would be negative e to the x over e to the x squared. I have an e to the x on the top and 2 of them on the bottom, so I'll cancel this one with one of those. I've got a negative 1 on the top and an e to the x on the bottom. So even using the quotient rule on that, it turns out to be exactly the same. Any questions? Okay. Can you do any algebraic simplification on this one? Nope. You're stuck. What rule would you use here? You could use either one. The way it's written right now, what rule would you use? You'd use the product. This would be the first and that would be the second. If you rewrote it as r over e to the r, then you'd use the quotient. So we've got first here and second here. We've got top here and bottom here. Let's look at this one here. Can you do any algebraic simplification first? Yes, you can, and you should definitely do that. Can you simplify it completely? Nope. So what rule are you going to be stuck using? You're going to be stuck using the quotient rule. Okay, so let's just do this. We're going to take out a t. I'm left with 3e to the 5t minus 6 over t squared. You can take out a 3, but you're not going to be able to cancel it with anything. So I'm going to cancel this with that. So s of t is the same as 3e to the 5t minus 6 over t. Did we do the algebraic simplification correctly? Make sure you did before you do the calculus on it. Now find the derivative. So what I'd like you to do between now and tomorrow, try and get started on the homework and get the answers to the 2 of these. I don't care which way you do it, okay, especially on this one right here. But see if you can get the right answer, simplify it. That's what we'll start with tomorrow, okay? Any questions? All right, have a great day.